Hi, everybody.
Good morning.
Hello.
You
Morning.
sound very awake and alert. That's awesome. I was just in another meeting, so I'm getting here a little bit late and not quite ready. I gotta pull up the lecture slides still. Do you guys know about there's something called the SF Scholars Program at San Francisco State that lets you, it's not for every major, but for the programs that have been admitted, and they're like 20 maybe different programs, you can, it's short answer is it's like you can get your undergrad degree and your master's together in 5 years. So it's kind of a fast pathway to a master's degree. What happens is you apply in your junior year, and you have to have a minimum 3.0 GPA. You apply in your junior year before you have too many units, and you start taking grad classes in your senior year. And so you're finishing up your undergrad classes and starting grad classes in your senior year, and then you take the remainder of your grad courses in your fifth year, and do research. Just like, I mean, you start the research as an undergrad, you kind of continue it as a graduate student. So you've already started your project when you're an undergrad, and then you finish in 5 years, and you've already got your master's, it's pretty cool, actually. This summer, we just got the Earth and Climate Sciences department registered as part of that program. So I'm pretty excited about it. That was the meeting I was just in. We were talking about that. I'm trying to learn about the different rules, and they actually make it sound they're really flexible as far as like, if you transfer from a community college and maybe you have too many units, well, they will work with you and figure something out. So anyway, if any of you are thinking about doing a master's eventually, and if you're a freshman or a sophomore, that's like, seems like really far in that's like really thinking ahead, but consider that and think about that as you're choosing your major too. And I still hope that, I know that we've got a couple potential majors in this class already for Earth and Climate Sciences, specifically geology. And I'm hoping that I might interest one or two more of you to try geology as a major.
Is it only for specific majors?
Yeah. So there's a list. I'll show you actually real quick. SF Scholars. I'll pull up the website and share my screen here. Here it is, list of programs. Let me just get on the right page. Okay, let me share. Okay, here is the page. SF Scholars Program. This is just eligibility, generic kind of thing. And then down below are all the programs. So accounting, anthropology, Chinese, all of these. Earth and Climate Sciences, engineering, ethnic studies, humanities, marine biology, philosophy, psychology.
My major's in there.
Which one is that?
Psychology.
Sweet. So yeah, you would go through a similar, so these links here are specific for that major, so you could open that up and get an idea. It's a roadmap basically, so you can get an idea which classes you need to take every semester to stay on schedule. It's possible to take longer to do this. It doesn't have to be 5 years. Like you could decide, for example, like let's say you're a full-time undergrad, but you only want to be part-time grad student. Well, you could stretch this out. It doesn't have to be just in 1 year that you do your grad work. But anyway, something to keep in mind, it's not really well advertised, and I think it's kind of up to the departments to tell you about this. So I wanted to just mention it so you guys have an idea that's a possibility.
Can you email this to us?
Yeah, sure. How about I just put it in the chat,
Yeah. What is
and
it?
then you can
Okay,
have
thank
the
you.
link.
What is it called again?
SF Scholars Program. It's
Oh, I
right
think
here,
I heard
San
of that.
Francisco State Scholars Program. Let me put it in the chat. Okay, there you go. That's the link to the
Thank
website.
you.
You're welcome. Wow, it sounds like I'm glad I mentioned it. It sounds like you're interested. Cool. Okay.
Yeah, I'm interested.
Sweet. It's a really, I mean, it's a really good deal. And plus it's also it's cheaper. If you're going to get your master's eventually anyway, this is like, it saves you money because grad school is more expensive than undergrad in general. Okay, so let me just, because I know I need every minute, it seems like, in this class. I'll ask for questions on the labs in a second, but I just wanted to point out, I told everybody that I was gonna stretch out the plate tectonics part of this class, and to give you, in part, to give you more time to finish this lab that uses Google Earth. It's not going to be the last time that you use Google Earth. I think probably we'll use it again in the earthquakes lab that we'll do. But I updated iLearn so that you can see plate tectonics was last week. Those are still here, all these same links, but I moved submitting lab 5B to this week. We'll start on earthquakes on Thursday and finish plate tectonics today, at least the lecture part. And then I hope to spend part of Thursday also looking at the Google Earth lab, that 5B lab. Is anybody having trouble getting Google Earth started or in using any of its elements? I'll just put that question
I am
out there.
actually not sure yet because I had just recently finished the other lab.
5A or the relative dating, you mean?
The relative dating one.
Got you.
So I'm going to start on yours today.
Okay.
I have not taken a look yet because it
Yeah.
took me kind of a long time to finish the other one because I wanted to get it correctly.
Got you. Good. If you can start that before Thursday, then that'll give us time to, I can answer questions on Thursday about anything. But
Okay,
if you
thank you.
follow those instructions in the lab, you know, line by line, you should be able to do everything on your own.
Okay, thank you.
Hopefully. Okay, so just to point this out, what I've done is I've basically plate tectonics and earthquakes and crustal deformation are going to be across 3 weeks instead of across 2 weeks. It's like a week and a half for each. I am not gonna, well, I don't want to promise that just yet. I was gonna say I don't want to start the earthquakes lab on Thursday, but I think I do want it to be available for you in case you're ready to start that lab. I have a feeling that some of you will finish the Google Earth lab kind of quickly. I mean, I hope all these layers that you're putting in, all these KMZ files that you're opening from within Google Earth, they have so much data. You could spend forever just like looking all over. I love looking at maps. I mean, that's probably part of the reason I ended up being a geologist, was just I loved maps. But looking at where on Earth are all these volcanoes? Where are all of the earthquakes? Why are they where they are? That's what I hope you're getting out of this, and I think it's just really cool. So I hope you're liking or that you will like checking out those KMZ files, checking out all those data. A lot of that data is you can download from, here, let me get out of this. A lot of that data you can download from the US Geological Survey. Most of this is from the USGS, I would guess. But simply, if you if you ever want to know if there's data of any kind available for use in Google Earth, you can Google the topic and add KMZ or KML, and those are the file types that Google Earth opens. And so you can check out, and you can just like find if any KMZ files exist for the kind of data you're looking for. And that's kind of where this came from originally. Okay, questions about Lab 5A or 5B for those who have started? Anybody? Oh, I see someone's going on the chat here. Well, that's, when is it due? Yeah, okay, so let me just look at my calendar. Originally, I said the 2nd, didn't I? So the 9th, yes. The 9th, that's correct. So aim for labs 5A and 5B for October 9th. I'm not gonna give you a ton of time to do the earthquake lab. It's gonna be shorter. So the earthquakes lab is gonna be less intense as far as like setting it up and getting, you're not going to have to get any layers in Google Earth or learn any new thing. You're going to work on a website. I might have you use existing data that you've already got in Google Earth. So when you upload those, definitely save your places in Google Earth. So when you quit, it will have all those KMZ files still in Google Earth for you and waiting. And the more layers you have in, the longer it takes Google Earth to open. That's why Google Earth wasn't opening for me fast enough last time that I tried, is I've got so much data there that it just takes a while. And I think it's also using the internet to sync with the data that you've got. Okay, so I just wanted to come over here and look at, okay, so here's the deal. So our first exam is coming up. Let me share, I'm gonna actually share my window again. Okay, I want you to be aware of this. It's been on iLearn for a while, but I've got the first exam. I'm gonna leave it open for almost a week. I'll open it on it will be a week, on Monday the 12th, and I'll close it on Sunday, October 18th. So almost a full week. It's going to be on iLearn. So you're going to submit, it's probably going to be a combination of true, false, multiple choice, and short answer type questions, maybe some matching. I think that's
Is it timed?
I think I will time it. Let me think about that, okay? Because I don't want, okay, there are a couple of reasons why I would want to time it. Because if I don't time it, you could spend a really, really long time looking up all the answers, like going online. You could spend a day trying to do this exam, and I don't want you to spend that much time, because I want to see, number one, I want to see what you already know, what you've learned from class. And so having you look up everything kind of defeats the purpose of the exam. So I don't want you to take forever. And I'm also thinking of you and like all the other stuff you've got to do, right? Because I know there will be a few of you, there's always somebody who wants to get everything perfect, and they'll take all that time. So I think I'm going to time it, but I'm going to be generous with the time. So I will try to guess based on how many questions there are, how long it'll take you, and maybe I'll double that amount of time. So if I think it's like an hour exam, I'll give you 2 hours. just so that you don't have to feel stressed out, because I also don't want you to stress about the time either.
Okay, thank you.
Sure. Make sure that when you're taking this, so because it's an online exam, and because I'm not having you do one of these proctoring services, those are so big brother, I just don't like them at all. I'm not going to do that. So it essentially is an open book exam, right? Because you're sitting there in front of your computer, you've got Google, you've got textbooks, you've got everything you could possibly want. That means that the questions might be a little like require thinking. It's not going to be just like boom, boom, boom. You're going to answer all these questions. You'll need to think and probably look at a diagram, answer some questions, like that kind of thing. So hopefully they won't be easy to look up answers. That's my goal. Again, because I want to test what you already know, not how well you look stuff up, right? Okay, so this exam is going to include everything leading up to that week, meaning we haven't started the rocks and minerals yet, but we will have finished the plate tectonics labs, and you will have finished your earthquakes lab. I'm going to make the earthquakes, sorry, I keep saying that, earthquake lab short enough that you can finish next week so that you don't need a lot of time, because I'm going to ask that you turn all of your labs in. Like if you have outstanding labs, your very, very last day to get anything to me is going to be the day that that exam opens. Because I want you to have finished all those labs before you start the exam. The labs are absolutely fair game. So just the topics. So there might be a relative age dating cross section where you have to put events in the correct order, or I might ask you to pull up Google Earth and answer a question about something, because presumably you already have that on your computer. What else? We've got there was the fossils lab that, what could I use out of that? That's a little trickier. That requires some geologic time. So I may ask questions about geologic time and understanding the differences between the Paleozoic, the Mesozoic, the Cenozoic. We can go back to the first week also, where we talked about observations versus interpretations. So basically facts versus interpretations, like what is an opinion, what's a fact, those sorts of things. Understanding those different principles that allowed you to complete those cross sections from your relative age dating lab. So that one, knowing original horizontality and the principle of superposition. And as long as you can explain those principles in words, don't worry about memorizing what those are called, like the word superposition. If you can explain that the layers on the bottom must be older than the layers on top, then I know that you understand the law of superposition. Okay, so I'm not about like memorizing the terms. If you're going to be a geology major, yes, I hope that you will remember those. But if, you know, a lot of you aren't. So I want to test your understanding, not the memorization. Plate tectonics is going to be a big one because we will have spent quite a bit of time talking about it, a week and a half. And we will also have spent a week and a half talking about earthquakes and faults. This is crustal deformation is going to, it's going to deal with faulting and folding rocks. So you will need to understand those things too going into that exam. So catch up on any, if you're behind watching any of these lectures, make sure, or any lectures on Tuesday or Thursday, right? Because I do lecture on Thursday as well. But make sure you're caught up on the lecturing, because no matter what's in your textbook, what I focus on in the lectures is what I think is most important. So make sure you're up on those. Make sure you finish your labs, and take all of the quizzes before the exam comes up. So you're going to have five quizzes online before that exam. So there's there isn't a quiz for every week. There's a quiz for every topic. So there was one quiz for plate tectonics, and there will be one for crustal deformation and earthquakes. If you haven't noticed already, those quiz questions are coming straight out of the textbook quizzes. And if you take the textbook quizzes while you're reading, that's a great way to do it, because they come frequently. Like you read a couple, it's like a couple pages of 8.5 by 11 sheet of paper sort of reading. You read about 2 pages that size, single spaced, and then it gives you a short quiz of 2 or 3 questions. Those are the same ones that show up on your online quizzes. So if you're practicing as you read, it gives you feedback. It tells you why some of those answers are wrong and why some of those answers are right. Practice there and then come and take the online quiz. That'll make those online quizzes a lot easier. And then hopefully you only need to take them maybe twice at most in order to get your high score. Of course, there's no need to take them twice, right? You can do it in one go. Okay. Any questions about the exam, the labs, due dates, anything like that?
Oh, I have like 2 questions. Like first, so is the exam like the quiz where it takes the highest score, or it's just one try?
This is gonna be one try.
Okay, got it.
Right. I'm just thinking. I want to make sure that that's, I'll let you know if that changes, but it's going to be a one try sort of deal.
Okay.
I was
Again,
curious.
so that you don't spend a forever on this, right?
Yeah.
Okay. There's another question?
Yeah, I was curious. I don't have the syllabus pulled up, but I was curious what the weight of the first exam was for our grade.
Sure. So there are 3 exams. This is the first of the 3. There's another one about another third of the way through the class. And then the third one will be during finals week. They form about 25% total of your grade, of your final grade. That means that each exam is worth about 8% of your total grade, of your final grade. The quizzes are 15%, so each quiz is about 1% of your final grade, the regular online quizzes. So those are each 1%. The exams are each about 8%, and the labs are 60%. So there are, so that makes them 60%. How many labs are there? I think
There's
there
15
are,
labs.
I think there are 15, right?
Yeah.
So that's 4% each. Yeah, that sounds right. So each lab is 4% of your final grade. But, you know, there are a lot of them. And don't forget that I'm dropping the 2 lowest lab scores. I'm dropping the 2 lowest online quiz scores. And my policy for the exams is this. I've been really flexible with due dates so far and accepting late work. I can't take those labs forever. So that's why I'm saying, like, I need them turned in the first third of the class. I need them turned in by the exam. That's going to be the same thing going throughout. But I just lost my train of thought. I was going to say, where was I headed, you guys? You're gonna tell me.
I think at one point last lecture you mentioned that if we attended every lecture, you were going to do something.
No, it's not attend every lecture.
Oh.
That's not what it was. Thank you. You did remind me. What it is if you turn in your labs, if you turn in 2/3 of your labs, so that's like 10 of them, if you can turn them in by the deadline, which is the week after we actually start the lab. So like for the plate tectonics lab, that's the 9th. So at the end of next week. If you can turn those labs in on those deadlines, just 10 of them, then I will drop one of your exam scores. Because I really would like you guys to keep up with the course material. I really would like everybody to be working on the plate tectonics lab right now. And to like, by turning stuff in on time, that lets you stay up to date with the class. So it's an incentive, I hope, to do that. And I think dropping your lowest exam score is a pretty good incentive, honestly. Yeah, so I hope that clarifies that policy. Sound good?
Yes, thank you.
Any other questions? Okay.
Yes. So the
Yeah.
very like for this like section, the very last day to turn in all the labs are before the exam, right?
Yeah, so I open, okay. So I said that I will open the exam. I'm just reading the
Yeah.
website here. Opens Monday the 12th, closes Sunday the 18th. So get me your labs. I said the last date to do the plate tectonics lab was Friday the 9th. Make sure I have all your earthquakes lab too by that Sunday the 11th. So I'm
Okay.
giving, so you have a little bit shorter time to do the earthquakes lab because I want you to finish before your exam. So I'm going to design it to be short for that reason. So try to get, if you can get your plate tectonics one done a little in advance, then it'll give you more time to do the earthquakes one. You definitely want to be ready to start the earthquakes one Monday next week. Don't leave that, until too late. And then it should be no problem to turn that in by Sunday.
Okay, got it.
Yeah, I made it Sunday just so, because I know that some of you have jobs and I want to make sure that if you've got like a Monday to Friday job, and I know it's hard to get other stuff done after you've had a full day work, like having a weekend to get that stuff done is helpful. So that's why I've added the weekend in there. And it says here, exam 1 covers chapters 1, 2, and 7 through 9. So those should be basically all the ones that are listed here. But like I said, lectures, follow the lectures and make sure you've done a good job with the labs. Oh, thank you. I'm glad we spent this time because I'm finally remembering to say, and you guys can still see my iLearn page, right?
Yeah.
I think so. Okay. So, did I put the key in here yet? Not yet. Okay, I will add the key now that people should be done. Wasn't the relative dating lab due last Friday? I think it was. I will add the key, but I have already added all the keys to all the older labs. So for example, exploring fossils, if you go back to the lab folder, you'll find a key down here. And I've given answers in all the keys are way more detailed than I ever expect from you, really. But I've explained everything. So hopefully if you had questions on how to do anything, the explanation will take care of that. Same with like the Earth history one, the topo maps. Where's the key? There's the key on topo maps. So there is not a key for the first lab because everybody's answers were so different that I decided that a key wouldn't really be helpful. So there's a key for lab 2, which is topo maps, lab 3, which is exploring fossils, and I will add geologic time today. If you haven't turned that lab in, don't look at the key until after you turn it in. I can see timestamps on your activities on iLearn, so I may check to see if you got it in before, if you looked at the key before you submitted, okay? So just don't do it. So I will put that up today. And then plate tectonics, I will add, I'll probably do 5A first because people need to have that done. And then I'll add 5B later, like next week, early next week, so that you have time. Okay, so those keys will eventually be there. They'll be there certainly with a few days for you to check those before the exam. Yeah, so I wanted you to make sure you knew those were there. I also gave you, I spent a lot of time, like a lot of time, giving you feedback on your labs so far. I really hope that you look at that feedback because I'm trying to help you. I'm trying to give you advice on how to answer the questions, like what kind of answer I'm looking for, like the level of detail that I'm looking for. And I explain kind of how I graded. I'm going by grading rubrics. So for each of these, and I can post those up too, so you can see what each question is worth in terms of points. But I assign points to every question. And so everybody is being graded exactly the same way. There have been some low scores. And since we're talking about it, or since I am, I'm going to say now that some of the work that I'm getting is not college level. So if you've had any labs that have scored, let's say, beneath 70 or beneath 75, somewhere in there, if you're getting a pretty low score on your labs, that could be the problem. It could be that you're not giving me enough detail, that you're not reading the questions carefully, that you're not providing everything that I'm asking for. Just go back and look at that feedback. Like I said, I'm trying to help you out. I have not said this is not college level work on anybody's lab, but I think that's true. But for those of you who are freshmen, and there's a fair number of freshmen in this class, for those of you who are freshmen, there's a transition period. I understand that. And so I'm also trying to help you out as far as your other classes are concerned. Ramp it up. Spend more time working on the labs, for instance. It does seem like some of them are rush jobs, like just going through it quickly, not going to any of the websites, not doing the virtual field trip, not watching the YouTube videos, and just trying to finish it as fast as possible. At least it looks that way to me. So just take that advice for what it's worth for you. Maybe it doesn't apply to you at all. Just, and if you need help, reach out to me, okay? Email me. If you want to sit down one-on-one, we can go through your labs. We can talk about your work. And I'm happy to give you individualized feedback like that, okay? So just let me know if you need more support in this class. Okay. What does this say? Can we still post the fossil lab today? Do you mean, can you submit it? Yes, just submit it. Like I haven't graded, oh wait, the fossil lab. Turn it in, and I do need to go back and grade at least one other person's because of a technical glitch. So get your labs in if you haven't. Here's your last chance. I'm giving you the opportunity before this exam to turn them in. So just do it. Just get them done and get them in. Okay. All right, let's think about plate tectonics for a while and less about grades. And I'm really all about learning and not about the grade grading. I want you to understand the material. Okay, da da da. We left off, I think we were talking about subduction zones and collisional margins. So we've already gone through divergent plate boundaries. I'm looking at the slides. Oh wait, you can't see that yet. I caught myself this time. Okay. I'm gonna stop this one and start this one. Okay, you can see the slide now?
Yes.
Okay, so we
Yes.
went through, thank you. We went through divergent plate boundaries. We talked about continental rifts and how those aren't plate boundaries, but they could become plate boundaries, like the East African Rift. We looked at the pillow basalts and watched that video, talked about Iceland, the East African Rift, how it's similar to the basin and range. And then I might need your help. I think we were about here. I think I left off talking about earthquakes. So all these, okay, let me know if I'm being redundant, but I think a little bit of review is good, and then we'll go forward from here. The earthquakes are these little starburst symbols that are kind of on the top part of this downgoing oceanic plate. And in this case, we've got an ocean continent subduction zone. Just a few, don't read the slide yet. Just look at the slide. Look at what the diagram is showing you. It's showing you subducting oceanic crust that is diving down. That's diving down. We've got earthquakes that are these yellow starbursts. We've got melting that starts above the subducting plate. Remember, it's not the oceanic plate that is melting. It's the mantle that's melting. So it's the water that is given off from the oceanic plate that lowers the melting temperature of the mantle rocks. So they're already really hot. They're like on the verge of melting anyway. They just need the addition. A little bit of water lowers that melting temperature enough that they can start to melt. And when they do, it's a basalt that is generated. It's a basaltic magma, just like the oceanic crust, just like the pillow basalts, just like Hawaii and Iceland, and all of the oceanic floor is basalt. Okay, those basalts are buoyant because they're molten. Anything like the mantle is super dense. The continent is even denser than melts. So melts, compared to all of those, are buoyant, and they start to rise up through whatever pathway they can find between crystals and in fractures and breaks in the rock, and along with other melts. They make their way up through the continent. And in this process, when they have to go through, pass through like a 30, 40, 50 kilometer thick continental piece of crust, they transform. They're changing chemistry over time, and they incorporate pieces of the continental crust. They melt those, or pieces fall in and partially melt in with the basalt. And eventually you end up with an intermediate composition melt. So this is like the Andes. I'm trying to give you like mnemonic devices to remember this. Andesite is the name of the intermediate composition volcanic rock. Rhyolite's the felsic version. That's the high silica one. Basalt is the mafic magma. And then an andesite is the intermediate composition. So it's somewhere between 60 and maybe 57 and 67% silica. And it's got intermediate amount of iron and magnesium. Anyway, this scenario where it's an oceanic plate diving beneath a continent is just like the Andes along the coast of Peru and Chile. And andesite is named for the Andes, right? The Andes is part of the name, if that helps you remember. So try to remember that that is the intermediate volcanic rock name, and that that's what comes out of these volcanic arcs when you've got when a continent is involved, when it's an ocean continent. Okay, so what is being dragged down the subduction zone with the oceanic crust? We've got seafloor sediments, right? This is saying sediments and other things are being, like the basalt, of course, the clay minerals, the radiolarian ooze that's at the bottom of the ocean, maybe some limestones, just muds. Those are coming down along with the rocks. Some of it gets scraped off on the edge of the continent. Like here's this little wedge of sediments that gets scraped off as that plate goes down. That's different from the mantle rocks that end up on the edge of the continent. We'll talk about that too later. Right now, I'm just talking about sediments being scraped off. So the sediments get scraped off, but some of them go down, and the crust itself has already been, it's already full of fractures and it's broken. As you stretch crust, right, it's rigid crust, so you can't really bend it. So when you do, when it is bent and when you stretch it, it cracks open. And so there are cracks and fractures in this crust, and the fluids and the sediments and all of that stuff gets into the oceanic crust itself. And so all of that is coming down. And so there's a lot of material that can give off water at depth. That also includes the transformation that some of the rocks undergo, that the rocks undergo when they get down to these really high temperatures. They metamorphose. And those processes also take the structural water that's caught up in the mineral itself. It's not liquid water. It's, you know, part of the mineral mica, like a muscovite mica or a biotite mica. Those have water in them, but it's just a hydroxyl group, an OH2 at the end of the mineral formula. And that gets driven off as actual water during metamorphism. The water enters the mantle. This what it's called is this mantle wedge. So it is a little piece of wedge, a little wedge of mantle that is above the subducting plate and beneath the continent. That's where all this happens. What else do I want to say? So the water lowers that melting temperature. You get the basalts that and then it passes through the crust and you get andesites out. Starts off as mafic, right? The mantle's ultramafic, but you partially melt it, you get a basalt, which is mafic. And then you transform it through the crust, the continental crust, and you get an intermediate andesite as a result. Okay. There's some other stuff shown in this diagram, like some other faults, like these are thrust faults. We'll talk about that on Thursday. And some folding and thrusting. So there's compression happening because we've got two plates that are colliding. And so there's a crumple zone, basically, along the edge of the continent. So if you notice in your plate tectonics lab, look to see, where is all the topography? Where are all the high mountains? They're usually, there are some in the middle of continents, but oftentimes they're on the edges, or they're on the former edges, the ancient edges of the continents, because of this crumpling and thickening of the crust. It's the same, you take a piece of crust this thick and then you compress it, it gets thicker vertically. Okay, the other thing I want you to notice is that the earthquakes start off shallow and they get deeper and they get really deep. If we look here, look at the scale here. So this is a map of all the earthquake epicenters around the world. You have shallow earthquakes in red. You have deep earthquakes in the yellow, well, intermediate in yellow, deep in green. So everywhere that you see those yellows and green colors, that's a subduction zone. those are the only places that you can get a rigid, breakable piece of crust at those depths, because the subduction zone, that subducting oceanic plate, goes really deep. It gets taken really far down into the mantle, 700 kilometers. That's really deep. So what is breaking? What is causing the earthquakes? It's the breaking of the actual brittle oceanic plate that goes down. And it's also at some very deep depths, it's the transformation of minerals to denser forms. So they actually shrink as they metamorphose. And if the minerals metamorphose like across a large area and they all shrink at once, you can generate an earthquake from that. Okay, so if I just go back real quick, the deep earthquakes are always inland from the coast if it's an ocean continent subduction zone. So we talked about there being deep trenches where the subduction happens, right? These plates bend and the trenches form where all this crust is being taken down the subduction zone. The shallow ones are near the trench. The deep earthquakes are closer to the volcanic chain of volcanoes, or the volcanic arc. They're further inland or further from that trench. So go back here. You can tell which direction the subduction zone is going. So just test yourself. Look at this subduction zone right here. It stands out to me. This is one of the plates that is subducting north of New Zealand, so northeast of New Zealand. Which plate is subducting here? Is it this one? Is it the Australian side? Or is it the Pacific side? Which plate is going down, Pacific or Australian?
Pacific?
Yes. The Pacific plate is subducting because the trench is going to be here near the shallow earthquakes, and then the volcanoes should be this way. So the volcanoes will be behind that, and the deep earthquakes are there. Even though there's no continent here, right? This is an ocean-ocean collision zone. You still knew that the subduction zone was going this way. Okay, how about this one? The Nazca plate or the South American plate? Which one is subducting? Remember
Nazca?
Nazca, yes. There are a couple reasons how you can answer that, right? You know that because oceanic crust is denser than continental crust. That's one reason you know that answer is right. Another reason you know that answer is right is because the trench and the shallow earthquakes are on the Nazca plate side, and the deep earthquakes are on the South American side. So the plate is dipping toward the east. Good. I think you guys have that. Okay, so subduction zones also have the largest magnitude earthquakes. So they have the potential to be the most dangerous kinds of earthquakes, just from the shaking or even from the generation of tsunami. I stopped myself from saying tsunamis. Tsunami apparently is the same in singular and plural. I don't speak Japanese, but this is what I've learned about tsunami. So don't say tsunamis, it's just tsunami. Okay. Bonus slide. Okay, so no, I'm going to skip to this one actually. I've said this already, but I just want to point it out again while we're looking at a map. Look at the Pacific Ring of Fire. We know the subduction zones are toward the continents, right? Nazca plate is subducting beneath the South American plate. The Pacific plate is subducting, it's kind of moving to the northwest. So it's subducting on the west and it's subducting on the north sides. Look at where the mountains are of the world. Where are the highest mountains? There are high mountains in the Andes, in the western US, all up through to Alaska. There are mountains or volcanoes, and all these island chains are volcanic island chains. There are high mountains here, the Himalaya. This is from a continent-continent collision. So India colliding with Asia causes a lot of this. Similar history of subduction all along from Europe all the way to Southeast Asia. That all was a subduction zone where we closed an ocean after Pangaea broke up. There are the places where you see high mountains that aren't next to a continent's edge. Like I'm looking at the Ural Mountains where I did my PhD. That's an ancient collision zone. That's a 385 million year old collision zone. That's why that's there. So it used to be the edge of a continent. Look at Norway and Greenland, and even northeastern Canada. Those mountains are there because of the collision that formed Pangaea, and they're a remnant of that. After it broke up, we still have mountains on both sides. That's the same with the Atlas Mountains here and the Appalachians. So everywhere there are high mountains, it's either because there's a current collision zone or because it's an ancient collision zone. Questions about that? I'm going to show you this movie again. Go ahead and ask questions if you've got them. I want to show this one again because I like the way that it shows dragging material down the subduction zone and then generating the melts deep down. So the earthquakes, do you see these fractures? These are the kinds of fractures I'm talking about that happen during the bending of the oceanic plate. And they should be parallel to the trench if you think about how the crust is bending. So we're bending that crust, we're cracking it open because it's brittle. We're dragging sediments down. We've got a whole wedge of sediments here. And then there will be earthquakes all along the top of this plate that's subducting. One more time. The water that's coming down is entering the mantle. It's melting the mantle and generating basalts that come up and feed these volcanoes. Okay. So shallow earthquakes near the trench, deep ones inland toward the volcanoes. Okay. So the closest subduction zone, so we had a subduction zone here. That's why I was actually looking, when we get to a map of California again, we will, I think, somewhere in here. Yeah, we will. It's so cool because California, just the geologic map of California records all three types of plate boundaries. There's evidence for all three types just in California, and it's really cool. Because we used to have the subduction zone right here in wherever you are, in Southern California, Central California, Northern California. It was all along this edge when the Pacific plate was subducting beneath Western North America. This is what's left, the Cascade Range. So Lassen is still an active volcano. Shasta, Medicine Lake are the southernmost ones that we have in California. This is part of the Cascade Range that is a chain of volcanoes that is still chugging along, still producing lava, still erupting ash, because there's subduction of that last little piece of the it's not the Pacific plate, that's the name of it today. It's the last little piece of the Farallon plate. You don't need to remember that exactly. But that was what we called the plate that subducted beneath California before we had the San Andreas, all right? But that subduction zone gave us the granites in the Sierra Nevada, gave us the Sierra Nevada, those mountains. And the north end of the Sierra Nevada is kind of here. So those granites actually dive, we can see them underground down there using geophysical instruments to look at the subsurface structure. So there are granites down there, but above them is the volcanic activity. So the volcanism is always taking place above where you would have granites crystallizing because they're coming from the same magmas. You've got molten, let's call it andesite. It's like an intermediate composition that's sitting down, let's say, in a single magma chamber or many magma chambers. If it's the size of the Sierra Nevada, it was hundreds of them, of small magma chambers where the melt was kind of stored. If that melt never made its way to the surface, it's going to end up crystallizing in the subsurface underground after subduction stops. And that's what happened. And that's what gives us those granites. But before that, we had volcanoes, and there's still volcanic rocks on either side of the Sierra Nevada that we can find that are a remnant of that. But if you want to see the action, now you looked at Mount Hood as part of your Lab 5A. So that's one of them that you've become more familiar with now. Here's Mount Hood from Portland. I would say Mount Hood poses some volcanic hazards to the city of Portland. And in fact, when I was looking at the topo maps, not even a geologic map, just at the topo maps, you can see evidence for flows that came very close to some towns. I'll be asking you about that at some point to look at that more closely, that is. All right, where are we? Okay, lost track. So Mount St. Helens, there was a famous eruption that you may know about. In 1980, Mount St. Helens erupted. I think I even have a little vial of the ash somewhere here on my desk. I didn't collect it. I wasn't a geologist then. But it was some family members lived in, I think they were in Oregon, and the Mount St. Helens ash fell. Everyone always collects it off their cars because it falls in a thick layer on your car. It was a huge explosive eruption. This is what Mount St. Helens looked like before. A nice pointy peaked volcano, nice composite volcano, an explosive type because of the intermediate composition lavas that it has are explosive compared to the basalts that you have in Hawaii or at the mid-ocean ridges. Those are pretty, the opposite of explosive when it comes to an eruption is effusive. I'll type that word right here since I can't. Effusive. Of course, it's in black. That's the opposite. So that's a gentle eruption type. But this was explosive, and this is the beginning of the eruption. It was ash that came straight out the top crater right here. And you can even see, like, these are lahars, another like a pyroclastic flow coming down the flank. So ash and other debris that's flowing fast and hot down the side of the volcano, ash and gases coming vertically up out and into the eruption column. But as the eruption progressed, because it happened over a couple of days, really, there was like a ramp up in the activity. I teach a lot of these details. I teach a volcanology class too, and we go into great detail about this kind of eruption. So they saw evidence of activity ramping up before this happened. And in fact, the death toll was a lot less than it would have been because they saw that activity and they cleared out an area around the volcano, and they blocked off roads so that no one could enter because they knew there was a potential problem. I'm going to get rid of this word now. What happened was there was a landslide that may have, there's earthquakes that are generated during volcanic eruptions from the magma that's moving through the rock. So there is seismicity there is shaking during a volcanic eruption. That led to a huge landslide on the flank of the volcano. And that's why there's this like kind of hole in the side of the volcano, because there was a big landslide. And then there was a lateral blast, an explosive blast that sent ash everywhere during the main event. So that took the pressure off of the magma chamber that was down there when that landslide happened. And all of it was like opening the lid on a 2-liter bottle of soda. You open the lid and you hear that the gases come out. You're basically, and before you do that, when you look at a 2-liter bottle of soda, you don't see any bubbles in there until you open the cap, right? Because the gas is trapped inside the liquid. That's kind of like a magma. The gases are trapped inside the liquid. But when you take the pressure off, like with a landslide, that's like opening the cap and the gases exsolve out of the liquid. Same thing. So the bubbles, the carbonation comes out of the soda and you see the gas coming out and it's coming up to the surface and then popping, going into the atmosphere. Same thing with the magma. The gases come up, the bubbles get big really fast. It's an exponential growth in the size of the gas bubbles, and that makes it explosive. So it's to do with the composition of the magmas, because you have to start off with a magma that has a lot of gas in it to start with. And that's true of felsic and intermediate magmas. Okay. Sorry, I tell these stories, I kind of like go on tangents telling you these stories about different things. Takes a while. Okay, so here's a picture. So Mount St. Helens is part of the Cascade Range. Here's Mount St. Helens. I think Mount Hood was this one. Here's the subduction zone. So this is the trench that this black line is following. And they always put the little triangles on the plate that's on top, that's overwriting the subduction zone. So the Juan de Fuca plate is being subducted beneath the Pacific Northwest, essentially. There are this is the Juan de Fuca Ridge. So there's a spreading ridge out here. They're small-ish. It's a smallish plate, but it's in like 3 main pieces. Down here in Northern California, this right there is where the San Andreas Fault ends. So that comes up and ends right there. That's called a triple point. Okay, what else? I want to point out the deep trench. Okay, so when you're looking at your plate in Google Earth and looking at the topography, you should notice that the deep trenches are all offshore, where it's an ocean continent subduction zone. You've got that trench that's offshore, where some of the deepest places on Earth are, right? That's to do with these subduction zones. So you have the deepest places and you have some of the highest places in the same convergent margins. Questions so far? I'll keep going if there aren't any. So it's like I predicted what was going to be here. Okay, so the Marianas Trench is here. It's the south of the Japanese islands. That is the deepest place on Earth. It is, you could shove Mount Everest down that trench and still have some room. So it's really deep. Someone might look up the elevation of Mount Everest, but it is less than 36,000 feet in elevation. So all of those trenches are associated with these subduction zones. All right, a little bit more on how the earthquakes increase in depth. Here's another cross section with the shallow earthquakes near the trench or along the trench, the deeper earthquakes down deep. Remember that in part, this is relatively cold lithosphere or cold crust because it's coming from the surface and then it's being shoved down this subduction zone. It kind of, my PhD advisor always called it, ready? He called it coolth, like warmth, but coolth. So I think, like, why not? Why don't we have the word coolth? It makes sense. Anyway, he would say that the subduction zone drags its coolth down, the plate brings its coolth down with it. So it's cold and brittle. So it's rigid, brittle, it can break. That's why I'm pointing these out. And look at where all right, we talked about earthquake epicenters. Those are these dots on the map that are on the surface of the earth. What do you call the point that is at at depth in earth where the earthquake starts? Because they don't happen on the surface. They happen beneath the surface. These points down here, you can call them either the focus. It says foci, that's the multiple of focus. So these are where the earthquakes actually start, or you can call it the hypocenter, HYPO center. That means the same thing. So whatever you can remember better, the focus or the hypocenter, epicenter, hypocenter, maybe that's easier to remember. They get deeper as you go down. Okay, so what makes an earthquake have a large magnitude? Number one, it has to be the bigger the piece of crust that breaks and shifts, the bigger the magnitude. So if you have a large area that breaks, for example, if we were to go over here to look at just the map of the world again, there was a huge earthquake in 2004, right close to Christmas. I think it was like the 26th of December. We had the Sunda arc broke and caused a huge tsunami. And I'm going to be going into those details about the tsunami during the earthquakes lectures. But it was like a 300-kilometer long section of plate. 300 kilometers, a huge section of that subducting plate broke. It was a huge earthquake. It was a magnitude 9.1, I think, or maybe 8.8. It was in the high 8s or the very low 9s. Really, really large. Okay, so great. You have a large earthquake that causes a lot of shaking. Let's go back here because I'm going to make a point. If that earthquake that breaks, if that piece of crust that breaks is really deep in the earth, well, a lot of that shaking, you can imagine that, like, if you've ever thrown like rocks in a lake or in a pond or in a mud puddle, you see the ripples emerge like around that rock when you throw it in, and they die off. They're larger when it, like, near where you throw the rock in, and it kind of dies off as it goes out. So the size of the little ripple gets smaller and smaller and smaller until you can't see it anymore. What that is it's losing energy. So some of the energy from that wave is going into other parts of the water, maybe into the surface and down deep. Only some of it is along the surface of that wave. So if the fancy word we use for that is attenuation. So the shaking attenuates, it dies off with distance from the hypocenter, from where the earthquake started. So here's the point I'm making. If the earthquake is very deep and it's very large, there's a lot of time and there's a thick piece of crust that those earthquake waves have to pass through before it gets to us, because we're sitting here on the surface. So it's not the very deep earthquakes that they might be big, but they're not going to cause a lot of damage. it is those large earthquakes that happen that are shallow that are the damaging ones. So if we think about our local subduction zone in the Cascades again, there is a big risk right now of a very large earthquake happening along the Juan de Fuca subduction zone and causing a lot of damage to Seattle, Tacoma, Portland. There could be it could be huge. And there is evidence in the geologic record. I think it was 1858. Don't quote me on that, but it was about that time when we have evidence of a really large earthquake that caused big vertical shifts. So like trees were sunken and died off. And we see evidence of a tsunami, like a big one that reached Japan at that time. And they can date those layers. So they think that the Juan de Fuca subduction zone caused that back in 1858. It could happen again. And these subduction zones are the ones that have the potential to get like a magnitude 9 earthquake. Our San Andreas Fault, probably we're not going to get much above an 8 because of just how these all work. So if that makes you feel better about living near the San Andreas Fault and not along the subduction zone, then that's a good thing, I guess, right? Just so you know, like, Japan has, they're really ready. We'll talk about them. I'll show you some evidence of some earthquakes in Japan. They're ready for some big earthquakes because they're on a subduction zone. They can get those magnitude 9 earthquakes. Historically, 1960 and 1964 were the big years for the magnitude 9 earthquakes. There was one in Chile and one in Alaska, and they caused huge amounts of damage. Those were both on ocean continent subduction zones. Okay, so that would be a good quiz question or exam question, is like, what kind of plate tectonic setting would you find the largest magnitude earthquakes at? And you might be given choices: mid-ocean ridge, subduction zone, transform fault, fracture zone, continent collision. I might give you like all those choices, and the best answer would be a subduction zone. Okay. Okay, so we've talked about, this is just briefly, oh wait, I think I skipped. No, that's good. Okay, I skipped this one, which just, while we're talking about subduction zone, I wanna mention continental collisions because they're important and because the Himalaya are an important mountain belt. This video shows the last part of the closure of an ocean that when India came close to Asia, it was closing a small ocean called the Tethys. And that's the same ocean that closed between Europe and all the way across the Middle East and through to the Southeast Asia. This subduction zone happened when you close that ocean and the continent actually collided with Asia, and it thickened the crust. So it's almost like two continents stacked on top of one another. You see India underneath the southern part of Asia. It's like double thickness. So this is some of the thickest crust on Earth, maybe 80 kilometers thick underneath the Himalayas. So the highest points on Earth are going to have the deepest roots beneath the crust. Isostasy, remember? Okay, so last slide for there. This is what I was showing you. India closing an ocean. So there was first an ocean continent subduction zone. So there was a chain of volcanoes there. And there's an arc there that looks just like the Sierra Nevada. It's full of granites. They call it the Ladakh batholith, or wait, it's got a different name in Tibet. That's in India. They call it the Ladakh batholith. It'll come to me. Okay, so we've got a typical subduction zone, just like we've been talking about. And then finally, India collides with the continental margin. Maybe there was a shallow sea for a while. And some of the evidence for the closure of India and Asia has to do with looking at the fossils in that collision zone. So some people date the closure of India with Southern Asia by looking at the end of the marine fossils and finding like the freshwater fossils that start up. There might have been a shallow sea for a while though. And so I think actually it was my dates. So this is probably what I'm best known for as a geologist, is dating the closure of India with Asia. So what I did was I took some rocks that were formerly part of the Indian continent, maybe couple 100 kilometers back in. And those were subducted beneath Asia, right? So maybe here, that represents the rocks. Well, some slivers of those rocks came back up the subduction zone. And they're right at that, on the surface at the place, at the margin where those two plates come together. There's a river that runs right along that suture zone. We call it a suture zone, where two continents are stitched together. And so I dated the rocks that came down the subduction zone and back up. And what I found was they had an age of about 53.5 million years ago down here. And I did some calculations and estimated that if you were to return the crust back up to the surface to the point where those rocks were just meeting the continent before they were subducted, that was about 57 million years ago. And so I cited myself down here. This paper in 2005, I think it's got like over 400, I think I'm on the way to 500 different citations that other scientists have cited that work of mine as being like the age for the collision of India with Asia. I think that's kind of cool. So I'm proud of that work. And of course, there are people all the time saying it's wrong. Totally, all the time saying it's wrong. And there are new papers coming out all the time with different dates. But luckily, people still cite my paper. Okay, transform plate. I skipped right over this. Okay, we're going to shift from convergent margins to transform plate boundaries. And I hope there aren't a lot of slides here. No, there aren't. So we're going to finish today. Finish these slides. I promise. Okay, transform plate boundaries. When I first started this lecture, I showed you this map and we looked at all the transform plate boundaries that were visible. Everywhere you see a yellow line. So there are like the San Andreas Fault is shown. The Alpine Fault is shown. The North Anatolian Fault is not shown. Okay. There are some other transforms up here, big transforms in the ocean, but most of them are on these offset segments of mid-ocean ridges. So it's these places where you've got ridge here and ridge here, and you need something in between, essentially. I should sketch that out. I will sketch that out later. Let me go through a couple slides more. I'll explain how that works. They're all over the place. We can't see most of them because they're underwater. Okay, San Andreas Fault is the prime example of a transform plate boundary, transform margin. This is probably the most beautiful examples of the fault. It's all on private land and you can't go and check this out yourself. But there's this scar. This is the Carrizo Plane. So it's down here. I think it's right in here. Wait, let me just put my glasses on real quick. It should say Carrizo. Da, 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 da. It does not. Okay, so I think it's probably right in there. Oops, sorry, the south part of the Great Valley. So right in there, it looks like this, like a knife, a hot knife went through butter almost, right? It's just beautifully expressed. It doesn't look like that everywhere, certainly. And you don't know of any place that looks like they're up here, do you? I'll show you. We get close on Highway 280, where the reservoirs are just south of San Francisco. The fault goes right through those. I'll show you some pictures. Okay, so there it is. We've got, so it moves, I've said this before, comes from the Salton Sea, east of LA, so through the Coachella Valley. The Coachella Valley is the place on the San Andreas where they are expecting that's where they're expecting the big one. And it's near LA and San Diego. So you should know about that and other populous places, but that is where they're expecting the magnitude 8 earthquake. There are other places along the fault where we can have earthquakes like that, of course. Even the Hayward Fault has the potential for a magnitude 8 size earthquake. But I wanted you to know that tidbit about Southern California.
Excuse me.
Yeah.
How would you describe an 8 earthquake?
A magnitude 8?
Yeah, a magnitude 8 earthquake.
A holy shit earthquake. It would be. If a magnitude earthquake hit right now, by the way, where are you sitting right now? Look around yourself. Where would you go if a magnitude 8 hit right now? Do you have a safe place to be? Doorways are not as good as you think. Get under a sturdy piece of furniture. Look around. Do you have a dining room table that's sturdy? Do you have a coffee table you can get under, or a desk, maybe? A heavy wooden or metal piece of furniture. Maybe even like a bathtub could be a good place. You want to be away from windows. You want to not be next to furniture that might fall on top of you. But look around yourself and think, where would I go if it started to shake? Okay, now I'll answer your question. You would see walls moving, like shearing, like side to side. You would see things falling over, like that floor lamp would fall over. My monitor would probably come unhooked and fall down. The china cabinet, or well, not the china cabinet, the thing with the TV in the other room would probably fall down. All of the vases that are on top would fall off because I still haven't put that sticky stuff on them so that they stick to the top of the furniture instead of falling down. Chimneys might break, like brick chimneys. They might actually separate from the home. Houses might shift off their foundations. Roadways would break. We're going to talk about this in more detail because I've got a bunch of slides ready for you, particularly about the Hayward Fault, because the Hayward Fault goes through government buildings, elementary schools. It crosses highways, many highways. It crosses water lines that send water to San Francisco. It's going to cause a lot of damage. Does that answer your question, kind of?
Yeah, it does. Thank you.
Good. I've only experienced a 6.9. So I was around for, I don't think I've told you this story. I was around for the Loma Prieta earthquake in 1989. I just graduated high school. I was a freshman in college when it hit, and I wasn't a geology major yet. And I remember looking outside and seeing my car, which was this old 67 Chevy, light blue, and it was rocking back and forth. I had the parking brake on, but it was just rocking. And I was watching TV, and the TV was on this thing. It slid out. It didn't fall off, but it slid out, and things were shaking on shelves. There wasn't a lot of damage it was my parents' house at the time, because of where we lived. There are certain places, depending on the kind of soils or rock that you live on, that will shake more than others. And so even though I was closer to the epicenter than San Francisco, I was in Campbell, so in the South Bay, like close to San Jose, there was much more damage in parts of San Francisco than there was in San Jose or Campbell, even though those were closer to the epicenter, because they were on fill. They were on loose muds and fill material near the bay. So we'll talk about that for sure. Okay, so the fault, where it comes for us, the fault comes across the Santa Cruz Mountains. The mountains are there in part because there's a little bend in the fault. So it bends to the left a little bit. And so imagine this, because the North American plate is moving south, and because the Pacific plate is moving north, that little bend causes there to be a little bit of compression there. So mountains are uplifted. That's the site of the 1989 quake. The epicenter was right about there. So between San Jose and Santa Cruz. The fault comes to up the west side of the coastal range, and it goes offshore in Daly City. Hopefully you guys know some of these places and that you live or have at least visited the Bay Area. I know a lot of you are in the Bay Area right now, and some of you aren't because of the online schooling, but you can drive out and check these places out. There's a beach that you can go, Muscle Rock Beach. You can go check out where the fault goes offshore. So it's outside the Golden Gate on the Pacific side. Then it comes back onshore like Tamales Bay, and it divides Marin from Point Reyes. Point Reyes is under the A in Andreas right there. And then it skims the edge of the continent up until it goes offshore. So it just kind of clips some cliffs on the way to Mendocino, and then it finally goes offshore to where it ends. The peninsula section, I should wait for some of this stuff. I'm telling you too much seismology now. The peninsula section hasn't had a really big earthquake in a long time. So peninsula section is kind of due. The northern segment is kind of due. But we released a lot of energy in 1989 that was beneficial to the whole area, because when you release the stress that is built up on the lock segments of the fault, that's a good thing. Okay. I wanted to point out a couple of other places where, and I know we're getting close to noon, just hang on with me. There are a couple other important transform faults that you will hear about. I've mentioned the Alpine fault in New Zealand. So it's between two sections of subduction zones. There's a subduction zone here, and then one here that are going opposite directions. And then there's a transform fault in between that is just like the San Andreas. Turkey has one. Here's California laid on its side like Turkey. This is the North Anatolian fault that is longer even than the San Andreas fault. So it's a major transform that causes a lot of damage occasionally on those earthquakes.
It looks like there's a question in the chat.
Oh, can you read it to me?
It says, what would happen if you were on the Golden Gate Bridge during an earthquake? Isn't the bridge prepared for these types of earthquakes?
I sure would hope so. Yeah, it should be engineered. It's going to shake, it's going to sway, and you're going to probably pee your pants if you were on the bridge. But Hopefully nothing would happen. Hopefully it would hold together and do its job. The engineers will have done a good job designing it. I hope it would just shake. In 1989, the Bay Bridge had damage, and that's why we have the new bridge, at least part of a new bridge across the bay there. And that was pretty major, but that was the only section of bridge that had any problems. The Golden Gate was fine. It also depends on, like, it's oriented, like the Golden Gate is oriented kind of parallel to, the Golden Gate Bridge is oriented parallel to the San Andreas. And that might help, actually, because the shaking is more likely to go kind of north-south. And then so if it crosses the Bay Bridge, which would cross perpendicular to that, that might experience more shaking than a bridge that is parallel to the fault. So that could help. Okay, thanks for that. I'm happy if anyone wants to read me questions from the chat, because like I said, I can't keep all those windows open. This is what I wanted to sketch for you. So I'm glad I have a little slide. Imagine a mid-ocean ridge that goes straight across, straight down the middle of an ocean. They're spreading, imagine spreading at different rates. So maybe this one's moving a little faster than that one. Well, that's gonna, over time is gonna mean that there are offsets on these segments. And so here's a little section of mid-ocean ridge, here's a little section of mid-ocean ridge. And because this side is moving to the right, and this side is moving to the left, this piece in between has to have a transform fault on it in order to accommodate the difference in motion. So that one's going east, that one's going west. So this needs to be, those arrows are wrong. He's got the arrows wrong. Oh my goodness, that's wrong. See, this arrow should be pointing to the left. Oh dear, I didn't notice that before. So this arrow right there should be pointed to the right, because that side is going to the right. This side is going to the left, so that arrow ought to be pointing to the left. So sorry about that. I will correct this slide after class, or just get rid of it and find a correct one. Shoot. Okay, this one is correct. Check this out. So maybe I'll just tell you what, I'll just do that, because that one's wrong. And I don't want you to learn the wrong thing. Okay, this is better. Imagine mid-ocean ridge here, mid-ocean ridge here. This piece of crust is moving to the right. This piece of crust is moving to the left. So there has to be a transform with that sense of shear forming between the two sections. And then it makes sense, because then if you're looking at this side, like this piece, everything's going to the right. So you don't need any fault. Like that's just an old scar from a fracture zone that is the scar from the transform. Same here. Both of these sides are going the same direction, so it's not a problem. It's just the piece in between. So that's where most of the transform faults are. Here's just a different way to visualize it. A little video showing mantle rising at the mid-ocean ridges, spreading, and how you have to form a transform fault. I'm glad the arrows are correct on this. You have to form the transform fault there. Oh, I forgot it switched. I wanted to show the beginning. Okay, it rises, it's spreading out. This side goes left, that side goes right. And then you pick up the next mid-ocean ridge. Is that clear to everybody? Or if it's not, let me know. Yeah, so it's showing San Francisco moving toward the south, LA moving toward the north. And over time, like that has shifted this piece of, so we have right out here, I can walk out and put my hand not too far on some granite from the South Sierra Nevada that has made its way up here. So it moves about 5 centimeters a year. So maybe 5 centimeters is about that much. It's a little bit every year, but, and sometimes with a big earthquake, it might be 6 feet all at once. It did in 1906, it did that, where there were ruptures. There were even 25-foot offsets in the north. Crazy. So these are just averages about the offsets. Okay. Yeah, I just wanted to point out the relative sense of motion so that you see the fast westward motion of these long arrows indicating a higher rate of motion in the northwest direction. North America moving to the west, but slower. And then the differential motion is this transform type motion that we get right there. Okay. And again, all these little transforms where we've got plates that are diverging, we're getting those transform faults. Oh, and the last few slides are simply hotspots. Okay, if you can give me 5 more minutes, we'll finish with hotspots. That would be great. If you gotta go, you gotta go. You can watch the last part of the video later. Here are the hotspots around the world. This is probably not all of them, but it's a lot of them. Notice that the Galapagos is a hotspot. Easter Island is a hotspot. Those are famous. Like Galapagos is famous for Darwin's travels, and Easter Island has those big moai. I can't remember exactly how you say them. The big stone men. They thought they were just heads, but they actually have bodies underground. Hawaii is a hotspot. Yellowstone is a hotspot. Iceland, the Azores. My family part of my family came from the Azores. That's right out there in the mid-ocean ridge nearby the Canary Islands. Yeah, a lot of other places. I want to show you just a little bit about Hawaii and Yellowstone because they're our hotspots. I'll claim them. Remember that these are generated from melts that we think come from the core mantle boundary, that D double prime layer of Earth, and that they generate a plume of magma that finds its way through the mantle, which is solid, and then it ponds at the base of the lithosphere. And then some of this melt can make its way through and feed volcanoes at the surface. We think all of these hot spots are in fixed places on the core mantle boundary. They don't move, which means that in the case of Hawaii, that if a plate is moving across, if we know the Pacific plate is moving to the northwest, right? And the Hawaiian hotspot right now is under the Big Island, or just south offshore off the Big Island would be the location of the hotspot now. The plate is actually going to keep a record of the volcanism as it passes across that hotspot. And so Hawaii works that way. I'll play this thing.
Not all volcanoes form at plate boundary. Instead, in the interior of
I didn't really want that. Hang on, let me mute that. I'll narrate. Okay, so this goes a little slow too. The magmas pond at the base of the lithosphere. They make their way through and they start feeding volcanoes. So originally there was the first volcano when this hotspot started. But the plate is moving constantly. And so it shifts and those volcanoes die because there's nothing feeding them anymore. New volcanoes start. You create a new volcano that's over the hotspot. The plate is still moving. I'll just be patient and let this go. The hotspot generates a new pulse of magma, feeds another volcano. There we go. There's a third island. I'm going to speed this up now. Okay, we get the idea. Oh, right. Plates change motion too. The arrows are going to the left. They're going to shift. The motion shifted from westward to northwestward over time. And so we see this in the Hawaiian Emperor Seamount chain of islands. There's a change in direction. So we see a line that goes sort of westward. And now we have a line of islands in Hawaii that has a northwestward trend. I'm going to skip here. So what that was showing you is this. Here's the chain of current Hawaiian islands that follows the northwest pattern of motion of the Pacific plate over the hot spot. Here's the Emperor Seamount chain. So these are former volcanoes that were eroded over time. They become, there's a coral reef that builds up, and they become just atolls. They're just a ring of kind of barrier islands with maybe a little bit of volcano left. That's what's out here. And a lot of them are underwater now. So these are extinct volcanoes, but we can go collect basalts and date those and get an age, and then establish how the plate motions changed over time, and we can get a rate using that as well. All right, then finally, last slide, Yellowstone. We have a hot spot underneath a continent. This is a place where we've had the super volcano eruption, because the magmas here aren't basalt. I mean, the magmas start off basaltic, but they have to pass through a continent, and they become more andesitic, more rhyolitic, and more explosive. So the Hawaiian chain, not explosive. Yellowstone, yes. And you can see the motion of the North American plate across that hotspot too, because there's a chain of volcanoes or volcanic centers or craters that go back 15, 16 million years ago that you find in eastern Washington or northern Nevada, southeast Idaho. And then the current Yellowstone National Park is where the modern caldera is and where the modern volcanism is. Has anyone been to Yellowstone?
I have.
Cool. Yeah, I've been there as a kid. I need to go back and check it out, because not since I've been a geologist have I checked that out. This is another place where there could be a very large eruption that would drop ash all over the place, over the entire country at some point. We'll talk about that again when we get into igneous rocks. I'll talk about explosive volcanoes and all that. Okay, I see that there are questions. I think I've answered all the questions in the chat. If anyone has questions, I'm done talking about the slides. I'm happy to go over anything, answer any questions about the lecture or about your tectonics lab with Google Earth. So I'll hang out and